Here, I'm going to show you how to quickly measure impedances with the Explore desktop, as it's a crucial step for every experimental setting. To do so, you of course need to connect to the device. Make sure that the device is advertising. This can be seen by a fast blink of the blue LED light, and press connect in the Explore desktop after typing in the device name. Once connected, you will be moved to the settings page. Here you can enable or disable channels as to them recording or not, and change the names. You can export and import device files and settings. I've created one to save us. To show you, you can change the name, but you can also select from the drop-down list. I need to update this last channel, press apply, and the settings are applied. Moving on to the crucial part, the impedance setting. I'm using a dry electrode setup, so I'm aiming for below 300 kilo ohm, which is much higher than the gel electrodes, but sufficient for the dry electrode setup to measure some rough signals that are associated with processes. As you can see, we are below 300 in all channels, which is very nice. It is, however, also because I've worn this cap a little longer. If you need to lower the impedances, try wearing the cap for a while, wiggle with the electrodes, or adding some gel to the reference electrode to get a good signal. Now to the final part. To visually inspect, go to the Visualization tab, apply the notch filter to filter out the power line noise, and have a look at the data. As we can see, the data right now is satisfactory. Let's have a look at artifacts. Eye blinks. Muscle artifacts like jaw clenching or neck movement. We can see there are still some artifacts, however, they're good for recording. We are good for recording, and we can move on to the experiment. Now let's move on to the oddball experiment. After navigating to the folder you should have downloaded from our GitHub page and activating your virtual environment, follow this command. Here, this parameter is the device. Make sure to change the ID, so these last few parts to match your ID, and type in a file name. Make sure that it's not one that already exists, and press enter. With the file name, we create 4 files, namely the ORN file, the metadata file, the marker file, and of course, the EEG file. The device will connect and the experiment will start. To give you an idea of what is happening, there's going to be a baseline condition, namely blue rectangles, which I should not respond to, and an oddball, namely a red oval shape, which I need to respond to by pressing space. Let's start. As you can see, the participants can rest between blocks and continue whenever they like. I'll see you in the analysis part. After completing your experiment, we can move on to the analysis. Make sure to be in your virtual environment and in the environment where you downloaded all the code from our GitHub page and type in this command. Make sure to change the file name accordingly. Some rudimentary filtering and pre-processing is being done, namely flawed epochs will be rejected. However, luckily for us, none of the epochs have been flagged. Moving on to the graphs, we can see that an unrelated brain area, namely the temporal parietal lobe, does not show any difference between the target and the non-target. To clarify, a non-target is the blue rectangle, the baseline condition, whereas the orange line represents the target, namely our oddball, the red oval shape. We can clearly see that in all of the somewhat related areas, we can see the P300. An event-related potential that has an onset 300 milliseconds after the stimulus is presented, which is shown in the dashed line here. You can see after around 300 milliseconds in CZ, as well as in CP2, CP1, PZ, P3, P4, also in POZ, not however in TP9, we can see the P300. For any other questions, please consult the wiki or write us at mentalab.com.